All right. So a couple reminders. I mentioned this last week, but there are 2 homework assignments due this week. One of them is kind of the normal web work thing, but the web work did not have a good intermediate value theorem question. And so there's a question in the note specifically marked that says, this is a homework question that I'm asking you to submit to Gradescope as well by Wednesday. So I'll show you that in just a second, but just be aware that exists. Make a note of that for yourself so you don't miss that. And just be aware that our first test is going to be next Friday. So, we're doing quizzes most Fridays in class. We did a quiz last time. We're going to do a quiz this Friday as well. You can see that here, right? We'll have a quiz in class. I usually try to do a quiz on the homework that was due Wednesday. So bring your notes. And we're going to have our first test the next Friday. And I've posted a bunch of topics and practice problems and things like that to Blackboard. So I'll probably show you that at a different day, but if you're interested in getting started with studying, which you should get started a week or 2 ahead of time, just sort of organizing your notes and things like that, then just know it's up there. I wanted to just show you something about Gradescope, and then we can do a homework problem, and then we can get started with the notes. So when I return, I'm going to grade quizzes through Gradescope, right? And I've already graded a couple there, and I return them through Gradescope. And I just wanted to show you that when you get them back, I usually send an email. And so for one thing, if you're not getting emails from me about things being returned, then you should check your spam folder and maybe try to mark those things as not being spam, because otherwise there's no point in me returning it to you, right? The whole point of these quizzes are to get some practice, me to sort of show you what you did correct, encourage you to improve some things that need work, so that when the test comes, like next Friday, you have nice solutions and you get a nice grade. And so when I pass it back, so this is quiz 2, for example, I just pass back here, I'm able to see whether or not people have looked at it. So on the right-hand side of the screen, all these eyes, I don't really want to show too many grades here, but everyone's eyes, right? I'm able to see if someone has seen or not seen the homework or the returned corrections. And it's nice to just see that people have looked at this, see what they got correct, and are trying to improve. In other words, maybe another way to say that is if people struggle with the course and way down the line they come and they say, I'd like to improve my grade. I don't know why I'm not doing as well as I would want to do. I always go back here and say well, are you even looking at the corrections? That's the first step. So I just want to make sure that everyone's aware that these are coming back with corrections and things like that, and that you should check them for it. I'll hand you back your hard copies on Friday, but all the corrections are going to be through Gradescope. Also notice how I can't circle it right here, but the top assignment on this page says intermediate value theorem question. I'll just click it open. And so this is the thing I was talking about. I'm expecting you to look at page 13 in the notes and do that example and submit it here. So it's going to be like a handwritten thing.
Quitting vaping day 3 days
Questions about what I've said so far? Sorry, that just threw me off. I'm going to keep going here in a second. Thoughts so far? All right, let me show you where that question is. Oh, the other thing, yeah, let me just show you where that question is quick. So in the notes, this is the last thing we looked at on Friday. This is the intermediate value theorem. We looked at this. We did a little example right here. And then right below that, it says homework problem, right? And I pointed this out on Friday, but I'll just point it out again. This is the thing on page 13 that I'm expecting you to submit to Gradescope. It's part of the homework this week. It's kind of unique. Usually the homework's just on Gradescope, so I just wanted to point that out specifically. Okay. Questions about that? I'm going to do a homework problem, but are there thoughts before we look at some homework? Just make sure my speakers are working here. Okay. So some of the homework this week is related to continuity. There are questions that look like this, for example. And we didn't do ones like this in class. And so I just wanted to do a couple like this to sort of give you the idea of how these are supposed to work, right? And so I have them saved in here. And let me just remind you about how we think about continuity before we look at that. Right, we're looking for these three things inside the red box for continuity. We're looking for the limit to exist at a point, right? If so, at point C, the function's continuous. If the limit exists at that point, if the function's defined there, and if the limit equals the function value. So those are the three things we're trying to think about whenever we have a question about continuity. And so that homework question looked like this. This is one of them, right? This is problem 3 from that homework. And yours might be a little bit different, but it might be the same actually in this case. I'm not positive about what yours looks like. But let's work this one out. Right? So we want those three things to be true. Where can I sneak those in? Maybe I'll sneak them in right over here. We want the limit as x. So the question is it continuous of 3, right? So we want the limit as x approaches 3 of this function to equal the function value there, right? And so, and question mark, let me put a question mark. The question is, does that happen? And it could help looking at the graph. We don't need the graph for these things, but I'm just going to draw the graph just so we know the answer before we even do it. And then we can kind of reason through why the answer is the way it is, right? So something's happening at 3. The function switches over at 3. And this first part, I'll do in blue. That looks like a y-intercept down here at -3, and it goes up 1 over 1. And at 3, it's going to be 0. So it kind of looks like this. That's that piece. And then the other piece switches over, right? And so the other piece I'll do in, how about yellow? You guys see yellow okay if I draw like that? It looks okay, right? The other one has an intercept at 3 and has a slope of -1. So it would look like this. So I'm going to fill this one in, and it goes like this. And the idea is like if we continued it this way, it would intercept at 3, but it doesn't exist over there, so we don't have to do that. Let me just pause there and see if that's okay. Does anyone see that that's what the function looks like? Can I clarify anything about that? This is what f of x looks like. Oops. Is that okay? Again, we don't need this picture, but I'm just trying to like draw the picture and reason it out before that, and then we'll pretend we never saw the picture and we'll answer it. I'll answer a question. It looked like maybe John wanted to say something. Any thoughts about that? Seems okay. So just looking at the picture, it's a continuous graph. And the idea is it's continuous because right where one ends, where one piece ends, the other one starts, right? They like line up with each other. In other words, if we were going to trace out the limit, let me trace out the limit in red here. If I was walking on the left-hand limit, let me get a different color here. If I was doing the left-hand limit, I would be approaching that point. The right-hand limit is also approaching that point. This is the function value, right? And so everything is lining up. And so we have that thing. And so just before we even write down an answer, we kind of know it's continuous. But let's kind of forget that we saw the answer and work it out. And so we're trying to do this thing again, right? We want to see whether or not the limit equals the function value. And so let's reason through that. So first of all, f of 3, in this case, we would plug it into the bottom graph, is 3 minus 3, which is 0. And so it's defined there, it equals 0. The question is that what the limit equals? So let's do the limit. The limit as x approaches 3 from the left, and then we'll think about the limit as x approaches 3 from the right. Right? Because both those things will tell us something about the overall limit. You with me on that? We do the left hand, we do the right hand, that tells you what the overall thing is. And when we approach it from the left, we use the blue graph. So let me maybe switch over to blue. That's going to be -3 plus 3, which is 0, right? We use the top graph, the top function, I should say. The top piece, maybe I should say. And when we do the bottom piece for the right-hand limit, it also gets the same thing. right, we'd have 3 minus 3, which is 0, right? We use the bottom piece there. And so all those things are equal, right? The function value, which is this, equal to limit. We all got equal to 0. And so the function's continuous there. That's sort of what we're saying overall. So I'm going to write down that final answer. So based on these two things, we just learned that the limit as x approaches 3 is 0. And I'll just squeeze the final answer right over on the right here. Can't do black. How about black? Since the limit as x approaches 3 equal the function value, this is continuous at x equals 3. Now I'll show you how to enter the answers in the boxes and stuff, or you can, I'm sure you can figure that out as well. But that's sort of the work behind what we'd be looking for. And that's generally, I don't need a graph on a test or a quiz or anything. This is a test or a quiz. I would be looking for the stuff I'm boxing in, like this kind of stuff. Right? Did you check the function value? Did you check the limit? Do you know what it means for it to be continuous? Questions about that? Want to clarify that at all? So if we were going to enter this then, right, just to be clear, the limit as we approach 3 from the left is 0. As we approach 3 from the right, it's 0. The function value is also 0. All these three things are equal to each other. And so is this continuous at 3? Yes. And again, kind of just looking at the picture, it's because the two sides lined up with each other. It's because one, right where one ended, the other one started. And so if we were tracing that graph, we wouldn't have to pick our finger off the page. And maybe that's obvious, but the point is we're trying to carefully think about the mathematical definition of why that's true. Anything about that I can clarify? Anything at all? I'm going to save this in the folder that I've shared with you all. I've shared a Google Drive with our notes in it. I put the weekly schedule in there. I'm going to start putting, when we do homework questions, I'm going to start putting the homework questions in there as well. So you'll have access to this later. So I think if I hit done, it'll save it. Yep. And then I'll just put it right into the folder where everything else is. Okay. So no questions about that? I'm going to do just one more a little bit quicker and show you one that's not continuous. And so, you know, the question's phrased a little bit different, right? It's sort of what you need to enter here is obviously phrased a little different, but you're still looking at the same thing. It's like, hey, check what happens at 0. Does the function exist there? Does the limit exist? You're doing the same thing. It's just asking you to enter different things in. And let's just do another quick graph of this, right? E to the x. So something, we're switching over at 0. E to the x looks like this at 0. Right, that's e to the x. And then x squared is before 0. And so that looks like this. And so e to the x starts at the point 1, but x squared goes all the way down to 0. Right, so there's a gap, in other words. If we were going to trace this one out, it's not continuous. If we were tracing it out here, we'd have to pick our thumb off the page or whatever and then start jumping up to the other piece, right? So it's not continuous. And it's not. I'm sorry?
If I can ask a quick question.
Yeah, go ahead, John.
So like if it's just less than, it's open, and if it's less than or equal to, it's a closed circle?
That's correct. Yeah. So this part here is telling you where to plug things into. So if x is 0, goes into the one with the equal sign. And so that's why that gets the filled in part. Yes.
Thank you.
Other clarifying things like that? And those are horrible. That picture is really bad, right? It kind of makes it look like x squared and e to the x look the exact same. They sort of have similar shapes. The point is, where one stops, the other one does not start. There's like a gap in between them because one starts at 1, right? E to the 0, just to be clear, e to the 0 is 1, where 0 squared is 0. So there's a gap there. There's a gap in the y values. It's this gap. And so the idea, if we just go through A, B, C here, I'm just going to look at these a little bit quicker than the last one. A, F, what is the question asking actually? Oh, why is it discontinuous? So f of 0 does exist. It equals 0. So that exists. That's not a problem. B, the limit as x approaches 0 from the left equals 0. But if we approach 0 from the right, it's at 1. And so this is the problem. Right? So that's the issue. And so we don't have that. Let's just run through the other ones. Both A and B, no, A is okay. And then D says D is not the issue. The limit doesn't exist. So it's really just B is the problem here, right? And so again, yes, if we just look at the picture, it's obvious it's not continuous. But what I'm trying to say here, it's not because the function value doesn't exist. It's not because the left or the right-hand limit doesn't exist. It's because the left and the right-hand limit don't equal each other, which means the limit itself doesn't exist. So just trying to think through some of those things. And there's a couple more that are similarly like this, right? And so you're just trying to look to see whether or not the two functions line up with each other at the connection point. And if they don't, thinking about what that means. Questions? Questions about that at all? Oh, I just saw this thing in the chat. So even though they are two completely different graphs, they are continuous because they intersect at the same point. So this must be a question from the last one. Sorry, I missed that before. I wonder if I can make a way to make a sound if the chat comes on. Doesn't it do that? Anyway, yeah, so it's not that they're two different, it's that the two pieces are different functions, but they line up with each other is what you're pointing out. Where this one on the screen right now, two different functions do not line up with each other at the intersection point, which makes them not continuous. The individual pieces are continuous, right? It's just the intersection point is not continuous. Sorry. Yes. Thanks for that question. Chris, other thoughts before we keep going here? Seem okay? That took a lot longer than I thought it might. That's fine though. That was good. And I went through Gradescope. I think that's all I really wanted to talk about. So I was going to pull up the notes again unless someone else has another question. So if you check out the test topics, limits at infinity are part of the test that's going to be, or is part of the test that's going to be next Friday. And then rate of change, the first part of rate of change is as well. So just in terms of thinking about what we need for the test, just so you know, it's going to be this page, and then the first type of this change. So probably through page 17 is what's going to be on our first test. So by the end of the day, Wednesday, we'll have all those things completed. And by the way, you're welcome to ask homework questions. Yeah, I see someone asked something. And so if there are other homework questions, we could do that. Sorry, I do have one question. When doing web work, do you suggest only graphing it if we can't figure it out normally? So graphing it is a nice way to do it, and it's a nice way to check your answer. But unless you're given a graph, there should be some other way to evaluate the question. So what I would say is don't rely on the graph, but use graphs to sort of verify your thinking and check your reasoning and things like that. But again, you should, what we're learning how to do is we should be able to do all these things by hand without a graph. Yeah. Other thoughts before we keep going? Okay. All right. So the last thing we're going to look at here is limits at infinity, like it says, and you can see two things that I want to point out. First of all the properties we've learned about limits still apply. So we're not reinventing the wheel here necessarily. We're just looking at a specific type of limits, which specifically are ones that have x or the variable approaching infinity, plus or minus infinity, right? And so there are techniques that we can use to solve these ones by hand, but what we're going to look at is the concept of a horizontal asymptote, specifically as it relates to the things down here in this box, which if you had pre-calc with me, we looked at this last semester, for example. You should be familiar with this stuff, in other words, but we're just kind of thinking about it in this new context of a limit. Okay. Someone say something? I thought I heard something there. No? Okay. So we're thinking about horizontal asymptotes, and we're going to illustrate the idea by thinking about 1 over x. So let's do that. So I'm going to create a couple tables here to evaluate 1 over x, and let's plug some big x values in here, right? Because you can see this limit is approaching infinity, right? And so let's plug some really big numbers into this function. And 1 over x is an easy thing to plug numbers into. You're just dividing by whatever you're dividing 1 by whatever you plug in, right? So let's plug in some big numbers. Let's plug in 100, 1,000, let's do 10,000. And then let's get kind of big, 100,000, right? And we'll do the same thing, but in the negative direction. Well, you can just see, because you're dividing by these numbers, the numbers are going to get smaller and smaller and smaller, right? But just to be clear, what we're trying to do here is we're trying to look at the left and the right hand limit. So this one on the left is a limit as x approaches infinity. Sorry, let me redo that. That's approaching negative infinity. So the concept of left and right means like going to all the way to infinity in one direction or the other. Oh, that one's plus infinity though, right? And then the other one is approaching negative infinity. And the numbers just get smaller and smaller, right? Like 0.01, 0.0001, 0.00001. And so the numbers are getting closer and closer to 0. And the same thing would happen in the other direction, but they're just coming up from the negative direction, right? So it's like minus 0.01, minus 0.0001, minus 0.00001. And so one's approaching 0 from the top, you could say like coming down to it, and one's approaching 0 from the bottom, like coming up towards it. And that should make sense because that's exactly what this graph looks like. And we've seen this graph a number of times now, right? There's like a horizontal asymptote right there. We've graphed this, I don't even know, 3 or 4 times already, right? So 1 over x does this. And so we just looked at the outskirts of that, right? We looked at way out here, or way out here, just by looking at the table. But if you look at the graph, don't focus on the middle part because that's not the infinity part, right? When we're approaching infinity, we're like way over here. We're like way out on the edges of it. And so when you look at this in pre-calculus, you talk about horizontal asymptotes, right? You talk about, hey, what happens way out on the edges of graphs? Is it approaching anything way out in the edges? And what we learn in pre-calculus is it happens wherever the denominators are 0, there's a vertical asymptote, right? And then whatever comparison between the degrees and the numerator and denominator, that's what makes the horizontal asymptotes happen out to the side. So basically what we just learned then, let me do this color here. I'm gonna write it right here. So based on all this information, the graph, the table, all of that, 1 over x has a horizontal asymptote at y equals 0, excuse me. Right? Because by definition, up at the top there, that's the definition of something being a horizontal asymptote. If the limit approaches something, if the infinite limit approaches something, we have a horizontal asymptote. right. What do you think? Questions about that at all? You guys remember this from pre-calc? Or is anyone confused about what I'm trying to say with the table thing? All right, so if you recall this back from pre-calc or wherever, it all has to do with the powers, right? The biggest powers control things when you start plugging really big numbers in, right? We're doing infinite limits here. And so we're thinking about plugging in big numbers. And so that's what's sort of being summarized in this box right here. It's talking about what happens in infinite limits, right? So let's say we have some rational function, which just means it's a fraction, right? So this is a fraction right here. And we have a polynomial in the top and a polynomial in the bottom, right? So both the things I'm highlighting right now, we're saying are polynomials. That's the definition of a rational function. And what this tells us, it says something about n and m, right? So let's focus in on n and m. Notice that n and m are in this piece of the definition, right? They're the powers that are in there. It's x raised to the n, x raised to the m. And so what this is telling us in the top here is number one, both the numerator and denominator are going to be polynomials. Hopefully we have a good idea what polynomials are, but now we've been using that term a bunch. And more specifically, the numerator has degree n. In other words, that's the biggest power. And the denominator has degree m. And if you're not familiar with that word from pre-calc, you don't remember that or whatever, this just means the highest power. So you just look at the highest power in the top and the bottom, right? That's all we're saying. As a quick reminder, we're looking at the biggest power in the top and the bottom, because when you plug really big numbers into a polynomial and you raise them to a power, the biggest power is really what's going to matter, right? If you plug, like, let's just look at these examples down here. Let's look at the example on the right here. The biggest power is on the top here is a 5. The biggest top on the bottom here is a 9. If you plug really big numbers into that x and raise it to the 5th power, it's going to be big, right? Think about plugging a million in, right? A million to the 5th is a big number, but a million to the 9th is so much bigger that it's going to cancel out the effects of raising it to the 5th power, is the way to think about that. And the 44x cubed, the 14x, those like don't even matter when you plug something like a million in. The biggest power is what matters. And so just looking ahead, that's one where the bottom and the power in the bottom is bigger than the power in the top, right? 9 is bigger than 5. And so that's this case right here. We'll look at this more carefully, but that's sort of the way to think about this table. All right, confident some folks remember what I'm talking about, but can I clarify anything else specifically before we look at a couple examples? I'll probably just do one. I hope this makes some sense, and then I'll ask you to think about the other couple yourself. Anything at all? I'm trying to remember if I graphed these already. I don't think I did. All right, I'm just going to do this first one, the one I was just talking about. So on this first one, this one right here, we look at the biggest powers, right? We just focus in on x to the 5th and x to the 9th, and we just think the biggest power on the top is 5, the biggest power on the bottom is 9. Since 9 is bigger than 5, or maybe I'll write it in the same way it says up there. It says 5 is less than 9, right? N is less than m. We are in case 2. right? So case 2, just to be clear, this one tells you what to do if the bottom degree is more than the top degree. And so that's where we are in this particular example. And that one just says, hey, if the top has the bigger or the smaller degree, then the outside limits are going to go to 0. This is just like the example we just looked at, right? If we kind of go back to 1 over x and we think about what this one looks like, this is case 2 below, right? The power in the bottom is 1, x to the first. The power in the top is 0, x to the 0. And so this is case 2. And when we looked at the graph, we actually graphed it. We see that it has a horizontal asymptote at 0. So we kind of figured that out looking at the table in the picture. And now we're saying, oh, we didn't really have to do that. We just realized this is case 2 above. And so case 2 tells us that the limit as we approach infinity is going to be the limit as we approach negative infinity, which is going to be 0. So it's going to have a horizontal asymptote at 0. Questions about that at all? And so again, back in pre-calc or wherever you saw this previously, and if you're in my class last semester, as we talked about this in terms of rational functions, one of the last things we looked at, we were defining it in terms of asymptotes, which is still true, but now we're just saying this is also the same thing as looking at the infinite limit, right? So it's the exact same thing, just kind of extending the idea to calculus now. Does that seem okay? All right. Gonna see if I can shrink this a little bit. Got a little bit too big on me.
Professor, I just have a kind of like a question.
Yeah.
So basically the first example that we did, the 1 over x,
Yep.
n would technically be 0, right? Because it's 1 to the x to the 0.
Yeah,
then-
that's right. That's
Okay.
right. So if we thought about 1 over x, this is obviously x to the first, but this is like 1 times x to the 0, right? Because this equals 1.
Okay. And then the horizontal asymptote would be at y equals 0, like we found.
Exactly. So if we're looking
Okay.
at that in this context, n is 0, m is 1, and so n is less than m, and so this is still case 2.
Okay.
Good thoughts, sir. Other questions like that? Still trying to make this a little bit smaller. Come on. All right. So yeah, just take a second to think about these other couple. I was gonna just let you think about these yourself. If we were in person, I'd probably ask you to group up. I don't think it's really worth doing something like breakout rooms. And so just take a second to think about these. I'm gonna maybe draw the pictures as you're thinking about it. I graph these ahead of time, and I'll just sort of start writing things down. But if this makes sense, it should be kind of easy. And if it doesn't, I'd love to hear a question. So maybe start thinking about how this works would be good, right? We're looking at the biggest powers. So in this first one, n is 2, m is 1, right? How does that one work? And the second one, they're the same. Can I do this? Let's see. Oh, I can. I can do like that, which is what I want to do. Cool. I'll throw a couple of pictures on here too. All right, so in that first one, the degree in the numerator is bigger, right? And so love to hear from someone, and I'm gonna go ahead and just try to call someone out. Love to hear from maybe Rashid. Are you there, Rashid?
Yeah, I'm here.
What do you think about the first one? We got the degree in the numerator is bigger. Which case is that? What do you think?
So it is 3.
Yeah. And what happens in that case?
Both of them are infinite, I think. So,
Yeah, exactly.
So 0, I think. Y equals 0.
So when it says, so this is case 3, and we're just kind of looking at this part, it's telling us that the limit as x approaches plus or minus infinity is just going to plus or minus infinity. In other words, we don't get a limit because it's not approaching something. It's an infinite limit. In other words, what this is telling us is that the top, because the top has a bigger power, the top grows faster than the bottom. Right? If you think about plugging 1,000,000 into the function that's on the left here. You would square it in the numerator, but in the bottom, in the denominator, you just leave it the same, right? So 1,000,000 squared is a big number, but you divide it by 1,000,000, and that's less. And every time you plug a bigger number in, the top grows quicker. And so there's no horizontal asymptote is all we can say here. There's no limit, so there's no horizontal asymptote. So the limit as x approaches infinity equals infinity, i.e. no horizontal asymptote. And you can kind of look at the picture and see that, right? If you look out to the right, it's just going to keep getting bigger. And if you look out to the left, it just keeps getting smaller. Not the best picture I've ever drawn, but if you graphed it, you'd see that too.
Is that the case for all problems where the numerator exponent is larger than the smaller one? There's
Yes.
always going to be no horizontal asymptotes for that case.
That's exactly right. Yep.
Hmm.
Because the top just keeps getting bigger. So it's not going to approach something. It's just going to get bigger and bigger and bigger and bigger. Other thoughts about that? Well, the third case. You there, Jorge? What'd you get in that third one?
Yeah, I'm here.
What's going on in this one? We've got the numerator and the denominator both have the same degree. What case is that?
1.
Yeah, so that's case 1. And what's that one tell us to do? It's kind of weird. Do you know what this notation means?
It's a fraction. The answer is a fraction.
Yep, it's a fraction. What are you dividing? It says AN and BM. What are those things?
The exponents.
So notice in this part right here that I'm circling, right? It's those things. So it's saying it's taking the numbers that are in front of the biggest powers and dividing those numbers. And so let me make that note right here. I would suggest making that note. What that says is it tells us to divide the leading coefficients is what that's called. In other words, if we go and look at this example, we're in case 1, right? And so this tells us to divide the leading coefficients. In other words, looking at this problem, when we plug 1,000,000 into x, we're cubing it in the top and the bottom. So that's going to be the same, right? It's going to be 1,000,000 cubed on the top. It's going to be 1,000,000 cubed on the bottom. And so what really matters are the coefficients that are in front of there, the 2 and the 3. Because you'll be multiplying the 2 on the top and the 3 on the bottom. So that's really what's going to control it because you have the same power. And so in this one, we want to divide the 2 and the 3 to get our answer. So this one tells us the limit as x approaches plus or minus infinity is going to be 2/3, which is the leading coefficient.
Is there any way you can like zoom into that problem and put them like in the middle?
Is that better?
Yeah, I just couldn't see anything. Thank you.
So that's the leading coefficient in the top divided by the leading coefficient in the bottom. Let me just pause there and see if that seems okay. And so just to be even more clear about that, we want to say this implies there's a horizontal asymptote at y equals 2/3. And that's what I'm trying to show in the picture. What I'm trying to say is this dotted line is at the point 2/3. And so way out on the edges of that graph, it's going to get closer and closer to 2/3. Let me just stop there and see if that seems okay. Actually, I just realized I think I need to put another homework assignment out there. Let me make sure that I'm thinking about this right. Yeah, shoot, there's a homework set called Limits at Infinity that I forgot to assign. So there's going to be, how many are in that one? There are 9 problems in there that are just like this one. Let me just look at them real quick to make sure that it looks good. Yeah. So I'm gonna have to adjust my weekly announcements there to just clarify that there's gonna be a second homework due, a second web work. Do that right now. Okay. Questions about anything? Chat looks clear. I got one out there. Yep, sorry.
I got a question. If you could scroll all the way up, where it says the fact, what does the L stand for again? Is that a limit?
So the question's about this part right here. The L is just if it equals something. So this is just telling us, and let me delete it so I can read it again. This part that I'm highlighting just says, if the limit as we approach infinity equals some number, so this is a y value, or if the limit as we approach negative infinity equals that y value, that's just the definition of having a horizontal asymptote at that point. So you see how, like, get rid of some of this stuff. Like this L and this L are where the horizontal asymptote are. So that's just telling us if we have an infinite limit, that means we have a horizontal asymptote at that point.
Okay, that makes sense.
Or the flip side of that is the definition of having a horizontal asymptote means way out on the edges, the function gets close to that point. Which again is something you see previously in pre-calc or whatever, but we're like relating it to this concept of the limit now. All right, questions about that?
So, for these limits at infinity, these 3 rules are gonna apply to all of these?
All the
Like-
ones that we'll see. Yeah, all the ones that we'll see.
All right, good.
We're only going to look at polynomial ones, and if I remember correctly, the ones in the notes are all polynomials. And there's nice applications like this one right here. Let's just look at this quick application. So this is talking about the photosynthetic rate for a soybean plant. And so this is a real function. This function right here, P of I, tells us, so it's how much photosynthesis this plant is doing given a certain light level, right? So just as a reminder, when lights shine or the sun shines on plants, photosynthesis occurs, which is going to increase as there's more light, right? So if it's a cloudy day, for example, there's not a whole lot of photosynthesis going on because there's not a lot of light reaching the plants, but as the light increases, you get more, okay? That's the idea. And so it's a rational function, and these are two things are both polynomials, right? This is a polynomial. This is also a polynomial. They're kind of ugly because they have fraction or decimal coefficients, but they're polynomials. And so the thing above there does apply. And so the question here says, estimate the maximum photosynthetic rate. In other words, how much photosynthesis could we possibly ever have? Well, this is begging us to look at the infinite limit. Let's see if we had just infinite amounts of light, what would happen to this function?
Can you repeat the question?
In the best conditions. Questions about that? Does this seem okay? What do you think about this? So we're going to look at the limit as I goes to infinity. This is now an application problem. What do you think about the limit as I goes to negative infinity? Does it make sense to look at that? What is that practically saying? If we let I go to negative infinity at this thing, what's that? Thoughts about that?
Yeah, like negative sunlight.
Yeah, like negative sunlight. Like that doesn't even make sense to think about, right? So I just want to point out that we're not going to look at the negative limit because what does it mean to have negative amounts of sunlight? It's like if it's 0, that just means it's dark. There's no light, right? So the negative infinite limit doesn't make sense. Just wanted to clarify that. We're just going to look at the positive limit. Negative light doesn't make sense. Okay. So let's actually answer the question though. So we're going to look at the infinite limit. The limit as I goes to infinity of this function. What do you think? Using the thing above there, which case is this?
You would divide the leading coefficients.
Yeah, so I'm hearing case 3 above there, right? N equals M equals 1 in this case. Because there's a power of 1 in the top and the bottom. Right. There's an I to
Wouldn't
the
that
power
be case
of 1.
1?
Say that again?
Wouldn't that be case 1?
Yeah.
Oh, I'm sorry. Did I say the wrong case? Yep, sorry. That's case 1. Thank you. And so we should divide leading coefficients. Case 1, N equals M equals 1. And so we'll divide the leading coefficients for this. So, all right, I'm going to do my final answer in black. I just wanted to sort of think about this a little bit before we did that. So the limit as I goes to infinity. Feel free to write as much of this down or as little as you want. Try to write enough down where if you aren't like fully following along right now, but you're writing everything down, it would make sense later. That's my goal. You know, the other thing is like on the quiz last Friday, as I was going around looking at people's notes, helping people figure out how to do the quiz, when you don't write down all the stuff in the notes, it makes doing the quizzes harder. And I was trying to like fill in people's notes as they're doing the quiz. The point is you should be writing enough down so that you can get the quiz questions right too. Anyway, sorry, I just started to mention that. Popped into my head. Okay, so we'll divide the leading coefficients. And so that's going to be 1.62 divided by 0.195. Did I get those numbers right? Yes. All right, here we are doing that. And I did this previously, and it's 8.3. And it's got a weird, it's got this weird unit, right? This unit, I forgot to mention that. It's a measurement of light. And so this is like, this weird thing. This is called micromoles. Apparently that's some light measurement. I'm not very familiar with light measurements, but anyway, it's a real function. It has that units. Don't worry too much about that. Just to know that we include the units, right? So the idea is if you are a soybean farmer or whatever, I don't know, maybe you're trying to get rid of soybeans. Maybe you have a soybean invasion problem or something. You might care about how much it might grow. And this is sort of an indication of how many micromoles is going to micromoles of photosynthetic rate at the most possible sunlight level. Questions? Maybe I'll just add that note in case people are like, what the heck did we just do? This is the max photosynthetic rate. Of a soybean plant. Okay. Questions? So we might care about the infinite limits in cases like that. What else is coming down the pipe here? This is actually probably a good place to stop and have our 50-minute class. As a quick reminder, one of our classes should be shorter. Or the other way to say that, I'm trying to have the Monday and Wednesday class add up to 75 plus 50. And so just making that work however it works. This is a good place to stop because we're starting another section. But what I would say is if there are other questions like about homework or the notes or the quiz, like maybe you looked at your quiz solution, you want to talk about that, I'm happy to stick around and talk about some more stuff. So I'm going to stop. If people need to go, I guess is what I'm trying to say. You're welcome to go, but I'd love to keep talking to you about whatever else is you need help with.
If so, could we do problem 13 of continuity?
Sure. Let's look at problem 13.
It's one of the ones where it's like at least one of your answers above is not correct. So like, I really don't know.
Okay.
It's wrong.
Yep. Let me pull yours up. Maybe I'll pull your specific one up too. Just in case it's different. So again, you're welcome to stick around, whoever, but if you need to go, you're welcome to go as well. Right. Let me do a screenshot. Okay. So yeah, this is the kind of problem we were looking at the beginning there. Just kind of practically speaking, right? These are both polynomials. So they're continuous other than x equals 1 for sure. And the question is, do they line up with each other at x equals 1? And so just practically speaking, 3 times 1 is 3 and 1 squared is 1. So these are not going to line up with each other, right? Like this is a y value, this is a y value. And so it's going to jump from 1 to 3 at that switching point. And so if we're thinking about what it looks like, we can draw it, but let's not look at it. Sometimes I feel like sometimes when I draw things, people get too dependent on like, oh, I need to draw something. Like there was that question like, oh, well, should you just draw these? Let's try not to draw it. So I should have deleted your answers at first. Let's just ignore those answers. Maybe they're right. I don't know, but let's look at it. So let's look at the limit as x approaches 1 from the left. So if we're to the left of 1, maybe I'll just draw this right here. Right, to the left of 1, we're using 3x. And to the right of 1, we're using x squared. And so to the left of 1, we do 3 times 1, which is 3. To the right of 1, we use x squared, which is 1. They're not equal to each other, right? 3 does not equal 1. And so that means the overall limit does not exist. And so just filling things in then, this is a 3, this is a 1. Looks like maybe you had those switched.
Yeah, I just am noticing that now.
And then, so the third one is a DNA, but the fourth one is not a DNA. Maybe you tried something different, but when you plug 1 into this tells you to use the top piece. So we would do 3 times 1, which is 3.
Yeah, I see my mistake now. I got it right. I had the left side of the graph and the right side of the graph were switched.
Okay,
Yeah. So my questions are answered at least.
great. Other thoughts about this one?
I just have a question on that one. Why is it 1 squared? You know what I'm saying?
Because we're approaching, that's the x value that we're looking at here. Right, if we look at all these limits over here,
Mhm.
we're approaching 1 in those limits. So that's why we're thinking about plugging 1 into these spots. Right. all
Even
these-
though that the condition for x squared has to be x is greater than 1, you can still plug in the
Right.
1.
So the function value is, we're not using it for that. We're just kind of
Okay.
thinking about what it's going to be as it gets close to that point.
Okay.
Like that, and if we're thinking about the graph, that would be the open circle. And so we're
Right.
getting really, really, really close to that point, but we're not like filling it in technically. We fill it in with the other one.
Okay.
But since it's a polynomial, it lets us plug it in there without a problem. So it's like, it's kind of like a cheat almost, like we're not really using this in the graph, but what are we getting close to, right?
Okay. I understand. Thank you.
Other thoughts about that? That was a good question. Right, keep in mind, when we're approaching from the left and the right, we're not thinking about being at that point. We're thinking about being really, really close to that point. So I understand the confusion, like why are we plugging in there? But we're sort of like thinking, like, what are we heading towards? Yeah. Other thoughts? Other specific homework questions that you want to look at, or anything for that matter? And
Yeah.
what I'll go ahead and do again is I'm going to try to, I think like if I hit done with this one, I can save this one in that same place, I think. Like I think I can do this. And then I'll try to put it into the Dropbox thing. Sorry, what were you going to say? Not the Dropbox, the drive.
So I don't know how to do question 6.
All right, let me pull yours up. Oops, wrong button. Okay, so then we have graph pictures, right? Let's see here. So this one's just asking you where it's discontinuous. So that one shouldn't be too bad. So we just think about tracing it, right? So I'm going to trace from left to right. Up, I have to skip over right here. So this is a discontinuity. If I was tracing the rest of it, I would go down here, but then I'd have to jump back up over here. So there's a discontinuity right here as well. If I was tracing this, I would have to jump up here and then jump back down here. So there's another discontinuity at that point. Same thing right here. All right, so all the places I circled on the x-axis, those are places where there's a jump, either a hole or the graph stopped and started somewhere else. So to me, that looks like discontinuous at x equals, let's see here, that's 1, 2, 3, -3, -2, 2, and 1, 2, 3, 4. Does that look right? Try that. Looks like you put -3, 2, and 4. So maybe you're missing -2.
Yeah, it works.
Okay. And we're just kind of using the tracing method here. We can talk about the reasons why they don't exist. So let me just do that really quick. I hope this will help someone maybe later. So at -3, there's a jump, right? At -2, there's an infinite discontinuity, kind of looking at the different types. And then at, I guess technically 2 would also be a jump because it jumps up to a point. And number 4, there's a hole. So we had to find some of these different types of discontinuities on the first or second page of continuity. So just kind of looking back at that to think about why. Other questions about this one or other homework questions?
Could we do that 13 one, the one from the notes?
I'll help you get started on that if you want, but since it's the only one in there, I'd like you to actually think about it. So
Yeah.
Let me go to the notes to that one. let me just kind of review the idea, and then maybe you can just do this one, right? So the idea is, remember the analogy. How do you know you're 2 feet tall? Because you used to be less than 2 feet tall. You're now bigger than 2 feet tall. So somewhere in the middle, you hit 2 feet, right? That it's a continuous function. You have to hit the middle of 2 function values. And the 2 function values there would be, when I was born, I was less. Now I'm bigger than 2 feet. And so somewhere in the middle, I hit that, right? So that's what's going on in this picture here. If you're wondering whether or not you hit n, which I'm circling, and there's a little bit of a delay there. Well, you pick some place less than that place, you pick some place bigger. And when I say pick, you're just kind of plugging numbers in to try to hit that. If you find some place bigger or less, that means you hit the middle point. And the example we did was with this function. Ken, I don't know why it's so delayed right now, but it's okay, we'll get through it. So on this one, we have this simple x cubed function that's being plotted there. And we wanted to know whether or not it eventually gets to 5,000. And so we just pick some numbers until we find one less than 5,000 and one bigger. And I just literally just plugged numbers in until I tried, until I got those things. And then I summarized it right here. Thing I'm boxing in right now that has appeared, that will appear any second there. All right. Turns out when you plug 0 in, you get something less than 5,000, 6. When I plugged 150 in, I got all the way up to 9,006. So somewhere less than 5,000, somewhere bigger than 5,000. It's a continuous function, and so it had to hit 5,000 in between. And that's what it says. That's what I wrote in words right there that I'm highlighting. I found somewhere less. I found somewhere bigger. This is a continuous function, and so it had to hit somewhere in between. And the continuous function thing is important. You have to say it's continuous. So then just kind of looking for, other questions about that at all before we look at the homework problem? And so you're just going to do the same thing here. This is actually just a different function for the photosynthetic rate that we just looked at a second ago.
Yeah.
And the question is, does this one hit 10? And so we just plug some numbers in, find one that's less, find one that's bigger, mention that it's continuous, and then write this exact same statement right here, just with different numbers, basically.
Okay.
Give it a second. This sent just with different numbers. And that'll be it. Take a picture of it, put it on Gradescope. I don't know who asked that. John, did you ask that one?
Yeah. So I'll give that a shot. So thank you.
Sure.
Have a good
Anything
day.
else, anyone?
I had a question on 8 on the web work.
You say 8?
Yeah. It's one with like a graph that begins to oscillate.
What's your last name, Kyle? B. Something with a B. There we go. Did you say 8? Yeah.
Yeah.
So I don't think the oscillation, let me just look at the question. Maybe it does matter here. Okay. Do you know which ones you're getting wrong?
Yeah, I'm getting the one that is f of 1 and f of 2.
I didn't look at the whole thing. Oops. That didn't help either. So f of 1 was one of the questions. Is that right?
Yeah, that's right.
So we just go to x equals 1 and go down to the graph. And so f of 1 looks like it's right there. Is that like in between 2 points? Is that the problem?
Yeah, I was trying to plug in points and I
Is
wasn't
it
getting any of them
It
right.
looks like minus 3.5 to me.
Okay, that's what I tried at first and it kind of is wrong.
Okay, let me look at the answer in a second. What was the other question though?
And then it was f of 2.
F of 2 also looks like it's funky. I don't know if you got a weird graph on this one or what.
Yeah, because like I was understanding how to do it. It's just once these 2 points came up.
All right, let me just look at the answers. Sometimes,
Okay.
so when these are randomly generated, occasionally people get ones that are very weirdly generated. This kind of looks like that situation. Let's just see. Yeah, looks like it wanted 3.25. This one was 2.5
Oh, wow.
though.
Okay.
But I don't know how you would ever get 3.25. Sorry about that. I don't know if, let me just make sure other people's aren't like that. I think everyone gets a different one on this. This may actually end up being the same one. What if I should email folks? Anyway, other questions, other homework questions? Anyone? All right, I'm going to stop recording this and I will post it.